Hello, my name is Meixner and I lead the software team here at Nuro. I'm excited to tell you a bit about our technology and what differentiates us. Today, I'll be talking about our autonomy stack and how we designed our software around our zero-occupant vehicle for a fast path to commercialization. Let's dive into our autonomy stack. Our fleet of autonomous vehicles is driving on the roads today, in daytime and nighttime, in different neighborhoods, different cities, and different states. What you see in this video is just a small selection of intervention-free drives from our Prius fleet on public roads. We have been operating in 3 states in many neighborhoods for years to ensure our technology generalizes. We run the exact same software in all locations. How did we get here? When we set out to build our stack, we thought deeply about the best path to commercialization. And we settled on a few principles that differentiate us. We designed an ML-first architecture, but with robust fallbacks for safety and the ability to leverage human intelligence to accelerate deployments. We prioritize safety over comfort, taking advantage of our focus on goods. And we optimize our autonomy stack to work in sync with our custom vehicle from the beginning. We applied these principles throughout our self-driving stack. In mapping, which provides information about the static world, perception, which uses the sensors to understand the dynamic environment around the robot, and prediction and planning, which let the vehicle interact with other road users and plot its own safe path. Finally, remote operations is what uses human intelligence to help with edge cases. Let's begin with mapping and localization. We build our own high-definition maps in-house. We first select a minimal set of routes to cover our mapping area. And then our operators drive these routes and collect data using our standard sensor stack. No special equipment required. The resulting data gets processed by an automated backend running in the cloud. And finally, we leverage a combination of robotics, ML, and human labor to build very detailed maps that contain road features such as lanes, traffic lights, crosswalks, and road signs. This information is more accurate and robust than trying to derive the same on the fly while driving. The result of this process are maps that are both highly detailed and scalable. In this video, we are showing the final maps we built for Houston and the Bay Area. They contain centimeter scale details for thousands of miles of roads. Our hyper-local deployments allow us to build maps to precisely cover the delivery areas rather than having to map entire cities. We have completely operationalized building maps and have over 71,000 linear miles of maps, which amounts to a region approximately 15 times the size of San Francisco. Next, let's talk about how perception utilizes all the sensors to understand dynamic objects around the vehicle. Our perception system uses both machine-learned and geometric approaches across different sensors to detect objects around it. All this information is fused together to detect pedestrians, cars, and cyclists. For each object, we do not only know its position and type, but also important other properties such as velocity, heading, and acceleration. Putting all of these together, the bot can track very complicated scenarios, such as cars and pedestrians in a busy parking lot, crowds of kids leaving school on foot and on bicycles, weaving through cars, a large group of cyclists that we encountered at night. Note how we track every individual cyclist accurately. It also works for static objects, such as this construction zone that we encountered also at night. Our perception system is an example of how we design an ML-first architecture with robust fallbacks. At the topmost level, we actively detect and track the most important objects for our driving decisions, such as other traffic participants, using state-of-the-art machine learning models. These algorithms improve continuously as we retrain with new examples, and they provide the highest fidelity understanding of what is going on around the vehicle. But not everything can readily be identified as an object. In the middle level, we densely label the scene with semantic classes, such as what is a drivable surface, and with motion estimates to detect anything that is moving in the scene. This both provides redundancy for important objects and handles things like overhangs, debris, or foliage that are not easily classified as an object. This is also done using ML. Finally, at the bottom, we reason about the scene purely from a geometric standpoint, where we can drive and what is a potential obstacle. In normal operation, each layer explains away the layer below it. But if a layer fails, we can rely on the next layer to keep us safe. You will see more examples of this fallback architecture later. Perception is also an example of how we prioritize safety over comfort. We tune our perception stack to err on the side of caution. So when we're in doubt whether an object is a plastic bag or a dog, we will just slow down until we're certain on what it is that we're dealing with. When we designed our custom vehicle, we thought about sensors from the beginning. Our bot has full 360 degrees coverage for both cameras and lidars. This allows us to robustly detect and track relevant objects in the scene, regardless of the configuration of the roadway or intersections, hills, or other environmental variables. The shape of the bot and placement of the sensors is chosen to have full near-field coverage of camera, lidar, and radar to minimize blind spots, even for challenging cases, like lane-splitting bicyclists or children interacting with the bot. Finally, thermal cameras are mounted in the front to provide extra protection for animals, pedestrians, and cyclists. For the sensors themselves, there are many options available, and each comes with its own set of trade-offs and fundamental limitations. You can see some of these limitations illustrated here. For example, cameras excel at providing understanding of the semantics of a scene. They allow us to finely distinguish different types of objects, but they're very sensitive to lighting conditions. At the same time, radar has little ability to understand detailed semantics, but it is unaffected by lighting conditions. Because each sensor has unique strengths, we put a full suite of sensors onto our vehicle. This both maximizes safety and reduces time to deployment. Here you can see how having a robust perception architecture with redundant sensing can handle adverse conditions. Nighttime and rain are both challenging for cameras. You can see the droplets on the camera and the reflections on the road. Our multi-sensor approach ensures reliable detections even when driving at night in the rain. This is not solved by hardware alone. Our software actively filters out artifacts like water spray and fog particles. Of course, challenges are not limited to rain. We also encounter fog, always a topic in the Bay Area. Sun glare, which is a daily nuisance in the mornings and the evenings in all our operating locations. And we also encounter heavy smoke during the California wildfire season. Now that we understand the world around us, it's time to drive. Prediction and planning are responsible for interacting with other traffic participants and guiding the path of the vehicle. Our prediction and planning stack has to interact with many other traffic agents, as you can see in this merge scenario. We use an ML-first approach to be able to handle these complex interactions. Our goods-first approach is especially helpful for neighborhood driving. Our bots can be extra cautious, drive a little slower, and even pull over for aggressive agents tailgating us. Because we don't have passengers, we can double down on ML by having robust fallbacks. The system always plans a fallback contingency maneuver that can safely bring the robot to a stop in case of any unexpected event. Our custom vehicle platform provides an additional benefit. The smaller footprint makes it easier to navigate local neighborhoods with narrow roads. Let's go a little bit deeper into how the system understands the intents of other agents and predicts what they're going to do in the future. Predicting the future is inherently difficult because it can unfold in many different ways. We address this by generating multiple hypotheses for each agent and rolling each of them out for 10 seconds into the future. For some agents, their behavior depends on us. Our system can also reason on how another agent will behave given our own course of action. We evaluate different scenarios to find the safest option to proceed. Understanding how other agents behave is a key challenge in self-driving. We heavily rely on machine learning here, but we also build in fallbacks based on our understanding of vehicle dynamics and map information. Other agents don't always behave sensibly and predictably. We need to handle that too. Here is a real scenario where some children started to circle our vehicle. Edge cases with irrational agents like this are very hard for any ML system to predict accurately. Instead, we detect when our predictions are not matching reality and notify the system to be more conservative. Given we do not have passengers in our vehicle, we can afford to prioritize safety and stay conservative for longer periods of time. Take this example where the bot reasons about cars hidden behind occlusion. It proceeds cautiously, creeping and modulating speed until it has clear visibility before clearing the intersection. I already described some examples of how we use fallbacks in different modules. We wanted another fallback for the entire system, so we built the parallel autonomy system with redundant compute, power, and algorithm design as a full system fallback. The parallel autonomy system can intervene with an emergency braking maneuver if an imminent collision is detected. This system is also active when a remote operator is assisting the bot for an additional layer of safety. In this simulation, we intentionally disabled the main perception system such that the bot is driving blind. We see that the parallel autonomy system identifies the pedestrians crossing the road and takes control. It brakes hard and is able to avoid the collision. In our third generation robot, the parallel autonomy system will also deploy the pedestrian airbag for the worst case scenario where a collision cannot be avoided. Our autonomy system is highly capable and an excellent driver. However, in the real world, there's no end to unusual and challenging scenarios that can arise. We also want to leverage human intelligence to best solve them. We do this by enabling remote operation of the vehicle. We have built a full software, hardware, and operational solution for remote assistance. The operators can provide different levels of assistance, from stopping the bot in case of a hazard to taking over full control. Remote assistance is a great fit for passengerless vehicles. The autonomy system can bring the bot to a stop in a safe location and wait for a remote operator to take over, all without impacting customer experience. Also, because we have tight control over our deployment areas, we can ensure that network connectivity is always available when needed. To wrap up, our autonomy stack is designed around our goods-first approach. We prioritize safety over comfort throughout the stack. We architect around an ML-first approach with robust fallbacks. Put together, this maximizes safety and minimizes time to commercialization. Being passengerless also enables us to use remote operations to handle edge cases without impacting customer experience. And our custom vehicle maximizes safety with its smaller footprint and fully redundant sensor stack. Here are some challenges that our autonomy stack successfully navigates on a daily basis, such as a hard intersection, a car door swinging open in front of us, double parked cars with another vehicle oncoming, an unparking truck at a construction site. Another car cutting us off. A large group of cyclists approaching us at night, some of them riding in our lane, and lots of jaywalkers, in this case with a pet in tow. What is often missed when describing self-driving technology is what it takes to validate that it is safe to deploy on public roads. Safety is important to us, so we have spent a lot of time and effort on our validation process. Before any deployment, we follow a rigorous process to prove that we are ready. This process starts with generating a set of requirements for each part of our system. This is another area where we leverage our hyperlocal deployments. Rather than defining generic requirements, we define requirements tailored to our intended operating area. We can focus precisely on the things that are most relevant for a given deployment. A benefit for both safety and time to deploy. We then verify our system against these requirements. Sometimes we find that we're not quite ready to meet our requirements, and then our engineers go back and improve the system. Turnaround time is critical in this phase, and so we use ML to accelerate evaluation of system readiness. Once the requirements are met, we launch, we celebrate, then we define new requirements for the next deployment. This is largely a data-driven process. We don't reinvent the requirements. We input new sets of data for the next deployment area and apply what we learned from the previous launch. When we define requirements, we leverage best practices from automotive, aerospace, and robotics. We start with the requirements for the overall system and then break them down into subcomponents. Here, we take advantage of having full control over everything from hardware to software to the human operator. We solve problems wherever they're easiest to address and then make sure that there are no gaps. Again, benefiting both safety and time to deployment. We use multiple methods to verify that we're meeting the requirements, with a few of the most common ones shown here. For each requirement, we choose a method that is most efficient and provides highest confidence verification. Let's take a look at some of them in more detail. We have the ability to re-simulate all our on-road logs with Nuro, even the ones that collected by our Prius fleet. This is a cornerstone of our validation strategy. It allows us to efficiently use the same on-road mile multiple times to keep testing and evaluating our software. We can also introduce artificial changes in the scenarios to ensure that the system is robust to minor differences. This type of simulation can only capture scenes that we have encountered on road. So we also have the ability to create synthetic simulations completely from scratch to create edge case scenarios that test the limits of the system. Like a person passing the bot on the right just as we are about to make a right-hand turn. What I just showed you is great for testing the software, but we also want to test the software together with a human operator. We built photorealistic rendering on top of our synthetic simulation to let software and human work together in a virtual world. We use this both for validation and for training. We build virtual worlds from our existing maps, such that our operators can train in the real deployment area. This enables creation of rich environments with pedestrians, cars, four-way stops, bus stops, jaywalkers, and narrow roads. We can adjust the time of day, encounter animals, as well as other bots. And we can even complete a delivery. Of course, simulation is only useful if it accurately reflects the real world. We use closed course testing to ensure that real-world results match our simulations. In closed course testing, we can enact our synthetic scenes using remote-controlled mannequins and robotic cars, and then compare to the simulation of the exact same scene. This is especially critical for surprise scenarios, such as the ones shown here, because they stress the algorithms, compute, and vehicle platform. While this testing is a very valuable resource, it is difficult to set up complex scenarios. So, we developed a way to let the real bot interact with virtual agents. This is a great way to test the real bot in complex edge case scenarios. What you're seeing here is the bot alone on closed course, but it sees a number of virtual pedestrians, marked by the orange boxes, and is able to interact with them, giving us the best of both real-world and synthetic testing. To summarize, we have developed a rigorous data-driven requirements process that can be targeted at specific deployment scenarios. a way to use our hyperlocal approach to optimize safety and time to deployment. We've already used this process to deploy across different states. We take advantage of our custom vehicle for a holistic approach to validation. We use both real-world testing and simulation to validate the hardware, software, and human as one system. All the pieces fit together perfectly, without gaps. Again, a benefit for safety and time to deployment. Finally, we leverage ML to accelerate evaluation and speed up iteration cycles leading up to deployments. Previously, we've covered our autonomy stack and validation for public deployments. Our goods first strategy was designed to enable a quick path to commercialization from the beginning. But what does it take to go from tens of vehicles to thousands of vehicles on the road? This is a question we've thought about a lot, and I want to tell you a bit more about how we're going to do this. To efficiently scale for mass deployments across multiple cities, we need to scale both the autonomy stack as well as the business. On the autonomy side, scale means enabling continued rapid progress on capabilities of the stack. This unlocks new geographic areas and operating conditions. A key to scaling autonomy is scaling ML. ML models and AV systems in general are only as good as the data used for training, validation, and testing. We quickly see all the common objects and scenarios in the world, but there's a huge variety of unusual things. A fallen traffic sign, an object thrown at the bot that occludes the cameras, a pedestrian losing a skateboard, or an officer riding a horse. In order to build a safe and reliable system, we need to iteratively identify issues and address them in the system. This process needs to be very scalable, as there's a huge variety of things that the bot can encounter in the real world. The traditional development cycle in the AV industry revolves around on-road testing and disengagements. We build a release, test it on-road, and rely on safety drivers to flag issues. Engineers then look at the issues and update the code and ML models. We deploy again and repeat the cycle. This doesn't scale because on-road testing is slow and expensive. What we do instead is to store, label, and organize all the data we've ever collected on-road. We then add more data from other sources, like targeted data collection, synthetic data, and data generated from simulation. We actively mine all this existing data for potential issues off-board. This includes full-stack issues that lead to bad behavior, but also more subtle module-specific problems, such as performance issues. This way, we can reuse the same miles to find new issues as the software matures. We close the loop entirely offline, iterating without having to collect new data or relying on on-road testing. Of course, scaling doesn't end with autonomy. We're equally proud of the software that we have built to support the operation of our fleet and our business. We talked a lot about making the bot drive itself, but there's a lot more to operating a fleet than driving. We have designed our third-generation bot to be operated and maintained remotely with minimal human touches. We build detailed mission plans for each bot that we can send over the air. We track the current status and position of each vehicle in our fleet in real time. We can also maintain the fleet remotely. We can start the bots in the morning, shut them down at night, diagnose and troubleshoot issues, download detailed logs including sensor data, and even install new software, all without somebody touching the bot. Autonomous delivery is a new experience for customers. We want it to be a great experience. This requires a platform that is built from the ground up for autonomous goods delivery, including both the hardware and the software. Our platform offers seamless integration with retailer order systems to make it easy for customers to place an order. After the order has been placed, customers can track them on mobile and on the web. And finally, when the vehicle arrives, there is an intuitive touchscreen interface and two-way audio communication with customer support in case it is needed. We cannot talk about scale without talking about security. For us, security starts with a trusted vehicle platform and a teleoperation system that ensures that Nuro is always in control. This trusted robot platform is backed by secure design, cryptography, and hardware security. And our bot is designed to also physically protect goods and detect any attempts of tampering. But of course, it doesn't end with the bot. We take great care to protect our partners' data and the private information our users entrust us with. We implement both technical controls, like encryption, and operational controls, like data segregation, to ensure that we are anticipating and preventing compromises and data leaks. Finally, we also take care with our own data. We use the same techniques to detect and prevent any attempts to extract our intellectual property. For all these areas, we verify security by emulating attacks from a well-funded criminal organization against our bots and platform. This creates high confidence in the entire system, from the robot to the corporate network. To summarize, to scale our robot deployments, we have built efficient feedback loops that can evolve our ML models without being limited by the cadence of on-road testing. Our third-generation vehicle is designed to enable a fully connected fleet that minimizes human touches. And we have designed a customer experience that is built from the ground up for autonomous delivery. What happens when we put all of this together? We see our bot driving safely on public roads. We see autonomous delivery of goods to happy customers. We see robotics better everyday life.